welcome back. A couple of weeks ago, a member of the Discord, Hugh, posted up some pictures of some old PCBs that he came across that were very interesting. He didn't know much about where they came from or what they went to or what they were even used for. All he really knew is that it said Bendix on it, which is our first clue. That kind of limits us to the early 1960s. And they had some really cool names like Emitter Follower or Full Adder. And well, me being the computer nerd that I am, I was absolutely enamored with these things. I was poring over the photos that he posted, and I started thinking it would be awesome to try and get schematics off of these because they looked like they were just single-sided PCBs, so they shouldn't be too difficult to trace out. But in order to do that, I needed to have them here in my hands. So I sent Hugh a message and I said, you know, if it's all right, could I borrow those for a couple of weeks? And, well, sure enough, he sent them here. So he sent 8 of these, and I'm only holding 1 because if I were to try and hold 8, it would be a disaster. But he sent them here and they're really, really cool. Now, I've gone through and I've tried to make schematics for each and every one of these. One of them I haven't quite gotten to yet, and honestly, they all baffle me. I am not the strongest when it comes to discrete transistors. I've done a lot of work with vacuum tubes, and I'm quite all right with those. And with the Centurion, I've been doing a lot of work with TTL level stuff, and I'm starting to wrap my head around that. But that kind of dead zone in the middle where it was discrete transistors and the manufacturers were doing all sorts of really wild things, I'm still very much so new at. So this was a massive learning experience for me, and well, I have hit some roadblocks that I can't wrap my head around. So I'm hoping that you guys can help get me pointed in the right direction or help get me over the hump and I can start wrapping my head around and understanding some of the more complex things that are going on. So let's hop over to the bench. We'll take a look at each of the boards that he sent, the schematics that I figured out from there. And well, I think it'll become painfully obvious when I became stuck. So let's hop over there and get started. So here are all 8 boards that Hugh sent, and they're just absolutely gorgeous. They're just beautiful pieces of engineering. Now, before we go looking at each one of these in more detail, let's try to figure out where they're actually coming from. And well, they're all labeled Bendix, and Bendix is a really interesting corporation. They started off, I believe, just building a very small part for something else, and then they grew their company from there, ultimately creating an aeronautics division, and the aeronautics division then started building computers. They built, I believe, the DL12 and the G-15. Both of these were vacuum tube machines, and the G-15 was particularly successful. The follow-up to the G-15 was the Bendix G-20. And this was now a fully transistorized machine that used core memory. Now, it's a little difficult to pin down the size of the words that were used because it's kind of all over the board. It uses anything from 15 bits to 32 bits to 50 bits. The arithmetic unit in particular is now doing math on 42 bits at a time, and that's going to play a very important role when we get to the full adder. But before we get ahead of ourselves with the full adder, let's take a look at this page here in the manual. We see that it shows the terminology for bistable states, and they have 1 and 0 as high and low, and they're showing that as 0 volts and minus 3.5 volts. But I think that's actually a typo. I think this thing is using negative logic. So minus 3.5 volts is 1 and 0 volts is 0. Now, it's highly possible that I have no clue what I'm talking about, but there is actually a typo in the manual that has caused a lot of confusion for me. And that is extremely obvious when we look at the AND gates and the OR gates. So let's pull those 2 boards out and take a closer look at them. All right, so I've got the OR gate board and schematic on the left and the AND gate board and schematic on the right. And well, you can see they're almost identical. As a matter of fact, the only difference that I can really find between these two is first the location of the key here that only allows you to plug it into one particular spot, as well as the direction of the diodes. And if we look at the schematics, well, that points that out pretty obviously for us. We have the diodes pointing in one direction on the AND gates and pointing in the opposite direction on the OR gates. And then we have our outputs coming off of where the diodes meet, as well as a pull up or pull down resistor depending on which gate it is. Now we know that this is an OR gate because, well, the chip literally says OR gate on it. And if we look at the schematic, we can see that our inputs come into the cathodes of our diodes, the anodes are tied together, and that is our output. Now, if we look at the manual, there is actually a page that's dedicated to AND gates and OR gates. And, well, we can see that it shows the OR gate as having two inputs into the cathode of the diodes, and then a pull-up resistor to 12 volts. And it says that's an OR gate, and that looks absolutely correct. But if we look at the diagram directly below that, we can see that that layout shows it as being an AND gate. So if we go back and we look at the truth table diagram for what they're labeling as the OR gate, we can see that it shows minus 3.5 volts, and if we follow the manual, that should be 0. And well, our output only goes to 0 volts or a 1 when both inputs are at 0 volts or a 1. And that's actually the truth table for an AND gate, not an OR gate. And so if we look at the actual schematic and the actual chip and what's marked on it, that leads us to believe that logic high is minus 3.5 volts, logic low is 0 volts, and it is a negative logic OR gate. The same goes for the AND gate. It's laid out exactly like is shown in the diagram in the manual as an AND gate, except that the logic diagram is backwards unless it is negative logic. But for these two boards here, it's pretty easy to figure out what's going on just based on the layout of the diodes and the resistors. But things get a little more complicated when we start getting transistors involved. And speaking of which, let's take a look at the emitter follower next. All right, here's the emitter follower board as well as the accompanying schematic. This was actually incredibly easy to trace out, but it also marks the beginning of me getting out of my depth. Now, as I understand it, an emitter follower is essentially just a buffer, and well, on vacuum tube circuits, I always used cathode follower buffers, but this being an emitter follower kind of threw me for a loop until I realized that, well, they're PNPs, and with PNP transistors, kind of everything is backwards of what you would think about on a NPN or, more importantly, a vacuum tube, which is what I'm most familiar with. And, well, I believe this is a fairly standard setup for a PNP emitter follower, so there's not a whole lot of surprises here, except for the 4 diodes that are just hanging out in the middle of this board. They don't seem to connect or have any influence on the emitter follower transistors, so I have absolutely no clue whatsoever what these diodes would be used for. Maybe it would be more obvious if we had more of the system or even the backplane to look at, but for now, these diodes are just big old mysteries. So let's take a look at the quad inverting amplifier next. All right, now we're getting a little more difficult with the quad inverting amplifier here, but here is the PCB and here is the accompanying schematic that I managed to beep out. It was fairly simple to trace out as well because, well, it was just the same thing repeated 4 times. Now, I am not unfamiliar with the idea of inverting amplifiers. As a matter of fact, the entire vacuum tube computer is built around the concept of inverting amplifiers. But vacuum tubes can't exhibit the same characteristics as PNP or P-channel transistors. That's just a total impossibility on a vacuum tube. Also, there's twice as many transistors per element as I was expecting. Now, as we discussed earlier, logic low and logic high are set to minus 3.5 volts and 0 volts. Which one is which is still up in the air. But I think a lot of this runs on plus 12 volts or minus 12 volts as well. But my theory as to what's going on here is that it takes a minus 3.5 volt to 0 volt input on the base, and then through this hilarious collection of diodes and resistors, it clamps the output in specific ways and gives us maybe a 0 to minus 12 volt or a 0 to plus 12 volt output coming out. Now, why that's important is still a bit of a mystery because, well, it's a small piece of a very large system, and there's a good chance that somewhere else in the system they need a stronger 12 volt signal. It's also entirely possible that it's using more than 12 volts, which may be why they have the transistors split the way they do. Maybe for driving maybe a paper tape punch or even part of the core memory system. But for now, let's set this one aside and go to the flip-flop board. All right, we're kind of getting back into a layout that I'm a little more familiar with, and that's because a flip-flop is, well, a flip-flop, and the design hasn't really changed a whole lot since the days of vacuum tube computers. And, well, this has a direct lineage to the G-15, so I imagine a lot of the design of this flip-flop was pulled from the G-15. But it works in essentially the same way. You have two transistors that are cross-coupled. The base of one is connected up to the collector of the other, and vice versa. Now, there is a whole lot of, I think, diode clamping and other resistor malarkey going on along the top, but for the most part, the left and right side are duplicates of each other. There is some interesting diode connections between the left and right side, and I'm not entirely sure why they're doing that. But aside from these three diodes at the top, at its core, right here in the center, it's just an SR flip-flop. And I love that that design is being carried over all the way into this because it's such an elegant, cool design that we actually see variations of this simple flip-flop design in modern computers. It's just the way to build a flip-flop, which I think it's really cool. So next, let's get into the big, difficult one, the full adder. Coming into this, the full adder board here was the one that I was the absolute most interested in because it feels like the heart of the entire operation. Computers are essentially just taking two numbers and doing something with them, adding them, subtracting them, doing Boolean logic on them. So this feels like such a quintessential part of the computer that I thought it was going to be an excellent way to kind of get in touch with how the G20 was built. And after a week of pulling my hair out, I'm thoroughly lost on it still. It is incredibly complex. It was certainly not easy to trace out. There are 40 diodes on this board, and combine that with 6 transistors and you've got some pretty complex behavior happening. So let's start with the most simplest approach to a full adder, and they actually show it in the manual here, and it's just a simple binary sums table. We have 2 operands coming in as well as a carry, and we just add the 2 operands and the carry together to give us an answer, which is a sum and a carry out. Binary 1 plus binary 1 plus binary 1 equals 1, 1. Plain and simple. Except it gets a lot more difficult than that when we take a look at how a typical adder stage is normally built. And that doesn't look like any full adder I've ever seen before. Partially because the layout is a little weird here and the way that they draw their logic elements is also slightly strange. Because the Bendix has a 42-bit full adder going on, there is an inherent problem with doing addition using cascading full adders like this, and that is that the carry signal has to propagate from 0 to 42, and this takes time. So this is what's called a look-ahead fast carry. It uses what they call leapfrogging. So they essentially look at what's happening at an earlier stage of the adder and use that to predict whether a carry is going to propagate or die in a later stage. And then they can send a propagate carry or a propagate kill signal up to one of those later stages. Now, I'm not very familiar with look-ahead fast carry adders, so I sat down with a member of the Discord, Chris. He helped me out tremendously with trying to wrap my head around this concept, but unfortunately between the two of us, we still couldn't wrap our head around what exactly was going on in the schematic here. It is a wild collection of diodes arranged in a way that didn't make any sense at first. I started trying to recreate it using logic symbols, and well, this is what I came up with. And well, there's two versions here, first of all. There's the positive logic version and the negative logic version. But you'll notice that neither of them bear any resemblance at all to the typical adder stage that we were just looking at. And that's because I believe what they're doing here is essentially creating a multiplexer that is being used like a lookup table. This is actually a technique that's used a lot on the Centurion. They use a little prom that is a lookup table for some swath of logic. And I believe that's the same thing that they did here. They just used a bunch of diodes to make a lookup table. So I went through and made a list of all the binary that's coming in and out of it, and we do have 14 different combinations of the 6 inputs that give us unique outputs. But no matter which way I organize the data here, I can't get the binary sums table to match up. I feel like I'm on the right path, but I just haven't found the destination yet. So actually, if you guys have any familiarity or idea about how this is functioning, how this full adder is doing its full adder malarkey, I would love to hear about it. Please leave a comment below or reach out to me on Discord and fill me in. Or I am building up a GitHub-based Wikipedia-style site for these specific PCBs, and you can just directly drop new information into there. Particularly if you have any information on cards that I didn't cover here. Maybe you have some in your collection. You can take some high-resolution photographs of them, you can send them to me, or you can add them directly to the wiki. Now, I only talked about 6 of these boards, and Hugh actually sent me 8. The remaining 2 are this one, which is a gated CPA, and this one, which is labeled as a DLO amplifier. Now for the gated CPA, I actually did trace out the schematic for it. This is also up on the wiki, but as soon as transformers start getting involved, I get totally lost. I am horrible with transformers. I have absolutely no idea what's going on with this one. As for the DLO amplifier, I haven't gotten around to tracing out a schematic for it yet, but there are high resolution photos of it up on the wiki. I will still take a crack at this in the future, but for now it's kind of on the back burner. And well, most importantly, I want to thank Hugh for sending these over. I had an absolute blast trying to figure them out. Even if the full adder here did send me down the rabbit hole into madness for a little while, they're just absolutely beautiful pieces of computing history, and they were just an absolute pleasure to look at and play around with. So I want to thank you guys so much for watching, and definitely let me know what you think about these, and let me know if you have any insight on them. But for now, I hope to see you in the next episode.